Bruce joined my lab, we were just getting started on moving from doing exclusively blind walking to integrating in perception, planning, mapping, etc. And so Bruce was on the was very open-minded about what he would contribute to the project in terms of making it as successful as possible. And so I was extremely grateful that he took on some of the things that maybe are considered not as glamorous as others, such as calibration, but in fact, he turned them into glamorous topics with a very deep analysis of these and new methods. So Bruce, that was very much welcome. And then he completed the thesis with extra work on planning. Bruce got his bachelor's degree at the National Taiwan University in 2014. He joined the master's program in robotics in 2016. He did interns at a few labs before he found ours, and I'm very, very grateful that everything worked out there. So he started his PhD in 2018, and Bruce, take it from here.
Cool. Thanks, Jesse. So first of all, I would like to thank everyone for your time to join my defense. And the topic of my dissertation is autonomous system for Lego robots from calibration and post-estimation to CLF reactive motion planning. So this is the outline of this presentation. I'm going to first give a quick introduction, then I will jump into three main topics: sensor fusion, Lidar tag, and optimal shape for Lidar post-estimation. And finally, an efficient anytime CLF reactive planning system that autonomously guides Cassie traversing through the wayfield at the University of Michigan. To have everyone on the same page, here are a few acronyms that we'll keep mentioning in this presentation. The first is CLF, control Lyapunov function. It is a Lyapunov function in a closed system. Therefore, any given time, there exists an input that makes V dot negative. So it converges to a desired state. RRT stands for rapidly exploding random tree. It is an algorithm for planning problems in higher dimensions. RKHS is reproducing kernel hyperspace. It lifts a point cloud to a continuous function where the inner product structure is well defined. We use it to overcome the sparsity of a lot of point clouds. RANSAC stands for random sample consensus algorithm. For people who are not so familiar with the technique, you can imagine it is similar to an iterative weighted least square method. It is used to estimate parameters of a mathematical model, which could be line, planes, or poses. Inside this algorithm, it tries to capture outliers so that the outliers have no influence on the estimates. In this video, you can see that the current controllers developed by our lab have enabled Cassie to walk on various types of terrains. However, you can see Jiunn-Kai standing behind there is still operating Cassie to provide velocity commands that speeds up, slow down, or to avoid obstacles, and for sure to walk from one point to another. It is important to notice that without a great baseline controller, even a skilled operator cannot operate Cassie over the wayfield. Having these great controllers makes my dissertation possible. Building on top of these controllers, the motivation for my dissertation is to enable Cassie walking autonomously over the wayfield. So I'm going to introduce a system that enables Cassie's autonomy. The autonomy experiments shown in this slide are guided by a CLF reactive planner, which will be discussed shortly. All the perception data are provided by a perception suite that I built in my first year of my PhD, and the data are processed in real time. So these are the key components to complete autonomy experiments. In fact, this is the system that we built for Cassie. It is indeed a huge system, so I'm certainly not going to address all of these in one dissertation. The green color indicates the components that I finished, and the orange is the work that I'm currently working on. So I will use a pink color to show which component I'm currently talking about so that you don't feel too overwhelmed. Like here, I'm showing the extrinsic calibration block. On the early autonomy work, it became very clear that our group needed fundamental contributions in the area of extrinsic calibration. So that's what the first part of my work actually focused on. Next, we noticed that our Lidar measurements had some systematic error, where I developed a global intrinsic calibration method to correct the sensor. As part of that, I realized that I could actually create a fiducial marker based only on Lidars, which would allow us to do things like look closer at night or in a completely dark environment. After building up a certain momentum, a certain amount of momentum in the Lidar tech domain, I also extended the work to target shape design so that the shape is designed specifically for Lidar pose estimation. Finally, I moved my attention to motion planning, where we propose an anytime CLF reactive planning system for terrain planning and an iMode RT star for higher level path planning. As a small fun fact, well, maybe you guys have noticed that I actually have done most of the areas in robotics, except what Jess is known for, contra theory. Did I intend that? No, I promise. I did not mean that, but it just happened to be that way. So, briefly speaking, the contributions of my PhD fall into three main topics. The first is sensor fusion, and the second is pose estimation through Lidar-based fiducial markers and motion planning. I first designed and built a perception suite for Cassie, which opens a new chapter for Cassie's autonomy. The perception suite is equipped with 2 cameras, 2 LiDARs, and 1 IMU. To fully utilize the sensor, we need to calibrate them extrinsically and intrinsically. For extrinsic calibration, we reduce 50% in projection error and 17% on its variance compared to a state-of-the-art algorithm. We also propose a unifying intrinsic calibration technique that is suitable for both spinning and solid-state LiDARs. Image-based fiducial markers have been out there for more than 30 years. Last year, we proposed the very first fiducial marker system for LiDAR sensors, called the Lidar tag. The system runs at 100 Hertz and is able to detect different sizes of targets while handling a full scan of Lidar point cloud. Next, building on top of the Lidar tag, we propose the first concept of optimizing target shape for Lidar pose estimation. We then utilize a global solver to estimate the target pose. Altogether, we achieve 3 centimeter error in translation and 1 degree of error in rotation when a target placed 30 meters away. The last piece of puzzle in my dissertation is the CLF reactive planning system on undulating terrain and an iMode RRT star for multi-objective path planning on large graphs. This is the list of publications in my PhD to support what I said and also to support what I'm going to present. Along with this publication, I release a bunch of GitHub sites, and this site shows the sites I released and currently maintaining. The first topic is the extrinsic calibration. Again, it is indicated by the pink color here. On the left, you can see the calibration is not so well. It's not so good, so that when projecting a lot of points back to the image, the curve is not aligned. On the right, on the other hand, is a well-calibrated system. After the calibration, we can know which points are corresponding to sidewalks, grass, or trees. And so that we have a semantic point cloud to build a semantic map. The problem of extrinsic calibration is to find accurate corresponding features from both sensors. It could be edges, planes, or vertices. Imagine, if we have an image and a patch of targets, if we would like to extract the vertices of the patch, what will we do? You might come up several steps to do this. Like first, we need to extract the edge points, like indicated in the red dots. Then you need to parse them into different edges. And here we use different colors to indicate for different groups of edge points. Next, we need to estimate the plane of this target so that we can project the edge point. Points to 2D. Then, because the points are then we can ransack different groups of 2D edge points into different edge lines. Again, ransack stands for the random sample consensus algorithm to estimate parameters of a mathematical model. And in this case, the model is a line equation. Meanwhile, it tries to capture the outlier so that the outlier do not affect the line estimate. So after ransack, those 2D ransack lines will have intersections, and those intersections finally will be our vertices of the target. The full process seems reasonable and doable, right? So now, if we show two more views of the target, the method we just showed suddenly become not so good because we don't know where the vertices should be or where the plane should be. Another important aspect is we are missing geometry constraints where we know the target should be a square or a rectangle or whatever the shape that we have. So we should know the angles and the lengths of each side. However, we do not impose these constraints while operating ransack. Another question is, what if we don't have enough edge points to ransack a line? Like in this on the right, there are only 9 points in total, and 5 of them are edge points. How can you do ransack for the top 2 edge lines? In this extrinsic calibration work, we introduce an L1 inspired template matching method to apply geometry constraints when estimating the vertices. By using the proposed method, we avoid identifying edge points and parsing them into individual edges of the target. And we also avoid projecting points back to the plane, as we just showed that the plane estimation will be noisy due to the systematic error. And also, the proposed method reduces 50% of projection error and 70% of its variance compared to a state-of-the-art baseline. The second topic is the Lidar intrinsic calibration, as indicated in the pink block. On the left is an image of the robotics building, and on the right is the accumulated Lidar point clouds. If we look from a larger scale, everything looks pretty and accurate. But if we zoom in, as we just showed, there is noticeable systematic error. So I turn my attention to Lidar intrinsic calibration to see where I can improve the literature. All the existing work postulates Lidar's mechanisms. The left is a 3-parameter model, and the right is a 6-parameter model. The number of parameters spans from 3 to 10. The reason why they are able to postulate the working mechanism of a spinning LiDAR because the mechanism is fairly simple for a spinning LiDAR. However, solid-state LiDARs are coming to the market. They have much more complex design. Design choices. Is it possible to design a calibration model for each of them, or is it even necessary? In this work, we propose to abstract away from the physics of a LiDAR, so that the calibration model can be applied to LiDARs with different working principles. We use the matrix Lie group to model the calibration parameters. It results in a unified view of calibration for different types of LiDARs. The model is mathematically proved to be well constrained, meaning only one unique answer exists. The proof further provides a guideline for target position. If you arrange for targets like a tetrahedron, the calibration model will only have one unique answer. To find a unique solution globally and efficiently, we formulate the problems as a semi-definite program through Lagrangian duality, so that an out-of-box solver can be easily applied. We show that the proposed method is robust to different levels of noise and also improve 68.6% accuracy compared to a factory calibration. This is a quick before and after results. You can see after the calibration, the measurement looks more accurate and precise when measuring a planar target. So now we have finished the block. Of sensor calibration. Next, we're going to utilize those calibrated sensors to estimate the robot pose. In the following, I'm going to introduce Lidar tag. The very first fiducial system, a fiducial marker system for Lidar sensors. Fiducial markers are some types of patterns that encode information such as websites, poses, or high-level comments. Image-based fiducial markers are out there for more than 30 years. Before the Lidar tag, all the fiducial markers are made for images. Here, we show the video of Lidar tag system running faster than 100 Hertz to detect different sizes of Lidar tags, while handling a full scan of Lidar point cloud. In addition to the first 2 points, we also applied the L1 inspired template matching method for pose estimation. Next, we leverage continuous functions into reproducing kernel helper space for ID decoding due to the sparsity of Lidar measurements. At the end, we achieve ½ centimeter error in translation and a few degrees of error in rotation. Why should we do Lidar tag? Why should we use Lidar tag? What's the benefit of using Lidar tags? Due to the intrinsic properties of Lidars, the measurements are not affected by ambient lighting. For example, if the scene is dingy or completely dark, it doesn't affect the detection of the Lidar tag. Or even in this kinds of extreme environments, the detection is still stable and we will not lose the track of the tags. So what exactly is a Lidar tag? It is composed of a 3D objects and a planar target with black and white boundaries. All you need to do is to put your image-based fiducial markers into the yellow region, and keep an eye on the clearance constraints, around each tag. This is a full system of the Lidar tag. It includes detecting the tags, estimating poses, and also decoding the IDs of the tags. Due to the time constraint, I will only introduce pose estimation and tag decoding. On the left, we first define a template with known target geometry at a Lidar origin. And the right is the patch of target points. Because we know all the dimensions, we know all the vertex information. Intuitively speaking, we would like to project the patch of the target points back into the template. Once we have the transformation indicating by the black arrow, we can actually have the inverse of the transformation, which will reproject the templates back into the target points, and that's essentially the target pose that we are looking for. Mathematically speaking, we seek to find a transformation from the target to the Lidar that minimizes the cost function. The cost function consists of the cost from each of the axes. For each axis, the cost is fairly simple. It is efficient for real-time applications. After we found the transformation that minimizes the cost, the inverse of the transformation is the target pose. Here is a qualitative fitting result of the proposed method. We place a target 14 meters away from the LiDAR. The cyan box is the template we project back to the target points. You can also see that the points are sparse, such that it is hard to correlate which point on the right is which pixel on the left. Next, we will lift the sparse point cloud to a continuous function to address the sparsity while doing the ID decoding. In this decoding process, we first pre-built a reproducing kernel helper space function library for each of the tag that might be put out in the field. We then extend the planar target to a 3D target based on the intensity values. In the runtime, we also build another RKHS function and then compute the inner product of each of the functions in the function library. The largest inner product is the ID of the target. This is one of the functions in the pre-built function library. You can see that it is no longer a planar target, but a 3D target. We apply a linear transformation that pushes back points with low intensity values and pushes out points with high intensity values to help the coding process. Given f as a function from the function library and g as a function built online, and k here is the squared exponential kernel. We compute the inner product of the two functions, and inner product is computed for each of the function in the function library. And the largest value of the inner product is the ID of the target. We have extensive results in the paper. Because of the time, we only show some qualitative results and one of the quantitative results. We put the tags in a spacious outdoor environment. On the left, you can see the experimental setup, where we have two sizes of tags, and the right is the detection and the decoding results. Next, we bring the tags indoor and intentionally stack boxes around so that the scene is cluttered. On the right is the detection result and decoding result again. This shows the extreme distances of the system. Again, you see the sparsity of a point cloud at different distances. Two sets of data were collected for quantitative evaluations. One is target face on to the LiDAR, and the other is the target rotated at 45 degrees as a challenging case. In both cases, we achieve less than 0.3% of wrong ID ratio. We achieve a ½ centimeter error in translation and a few degrees of error in rotation. You may see that 14 meters is the maximum range for this square shape and the Valentine 32 beam LiDAR that we're currently using. How can we push the limits of the post estimation of the LiDAR tag? This brings us to the domain of target shape design. Let's revisit this slide again. You can see that over the past 30 years, shapes that are used for photoshop markers are symmetric. Symmetric shapes have no problems or troubles in images because they have dense and structured data type. However, for LiDAR data, you can see the LiDAR points on the right are far less than the left. Due to sparsity, the fitting results suffer from the quantization uncertainty of LiDAR points. The pose is actually undefined if no pattern on the target. Building on top of the LiDAR tag, we propose the concept of optimizing target shape to eliminate problems caused by quantization uncertainty and sparsity of the LiDAR image of a target. We then formulate a pose estimation problem as a QC-QP so that it can be solved globally and efficiently. We achieve 3 centimeter translation error and 1.1 degrees of rotation error, even when a target is partially illuminated and placed at 30 meters away. Left figure is the target 30 meters away, and the optimal shape is the red irregular shape on the right. You can see there are only 9 Lidar returns on the target, which are used for post-estimation through the global solver. The right shows the fitting results. We have extensive qualitative and quantitative results on the paper. Well, again, there are not enough points to rank at the top 2 edge lines. So now we have finished sensor calibration, sensor fusion and post-estimation through Lidar-based version markers. The next topic is CLF reactive motion planning. So again, the CLF stands for control Lyapunov functions, which are Lyapunov functions for closed loop systems. So at any given time step, there exists an input that makes V dot a negative. So it converges to a desired state. This is the video about the reactive CLF planning system that autonomously guides Cassie through traversing the wave. The environment is totally unknown and unmapped to Cassie at the beginning. We set the goal at the far end of a rally. The white line links Cassie to the goal. The planner is guiding Cassie to stay in the valley and not to walk onto the hump. The map is building online while Cassie is autonomously navigating. The highlighted area is the local map, which computes into additional information such as local gradient or smooth out the map. The green line is Cassie's trajectory. All the perception data is processed online, and ultimately the CLF reactive planning system successfully guides Cassie through the wave field. So, what is a reactive planner, and what's the difference between a reactive planner and a standard planner? For a standard planner, we're given a intermediate goal, and an RT star or A star planner provides a list of collision-free waypoints. Then we will connect the dots with lines to form piecewise linear paths, which are not feasible for all the robots. We will then perform polynomial fitting to smooth out the piecewise linear path. However, the process is expensive in the sense that the curvature is not known before evaluation. So we might need to compute this step multiple times. After we have the smooth polynomial path, we will need a controller such as PID to track the position. Then the robot starts moving, and the robot will deviate due to some tracking errors or some imperfection of the model. And until the deviation is larger than some threshold, we need to proceed. We need to execute a replanning process, which is expensive because you need to redo everything, things like generating waypoints, connecting dots. This happens quite often on our highly agile open loop unstable Cassie platform. Then the polynomial fitting again, and tracking, and then we reach the goal. On the other hand, reactive planner, we generate feasible path directly from a control Lyapunov function that was designed for our robot. We do not need waypoint tracking, so that we don't need an extra PID control to track the path. That's being said that we handle robot deviation ourselves, rather than hand it over to a controller. The CLF automatically adjusts the velocity and orientation based on the current position and orientation of the robot. Therefore, the low-level controller running on Cassie is tightly coupled with the planner. And the benefit of it is that we can send terrain properties such as friction, type of terrains, or slope to the controller if needed. This would help us tackle undulating terrains, staircases, or even unstructured steps. We populate the space with vector fields as shown in the arrows. Then the vector field will move the robot forward. And when the robot deviates, the vector field will automatically adjust and steer the robot back, and that's why we have automatic replanning. Then we reach to the goal. So this reactive planner planning system is inspired by Dr. Park and Professor Kuipers. They have done a great work on demonstrating the potential of this workflow on a Vulcan wheelchair robot, which is a differential drive vehicle. The black dot is the target position, and the arrow is the target pose. The green curve is one of the trajectories, but if you are at other different locations, the CLF will automatically give you other trajectories at no cost because it is a vector field. So there are a lot of trajectories converging to the desired pose. This is not a problem for differential drive vehicles because they can change controller commands at any given time. Whereas Cassie, which takes piecewise constant as inputs, she cannot change her speed or orientation in the swing phase. This leads to a jittering motion when Cassie is close to the target. For example, at T1, the vector field will give commands to go bottom right, and T2 will go to bottom top. I will go to top right, and T3 will go to bottom right again. And it is all because Cassie cannot change its controller commands in the middle of the step, so it tends to overshoot. In light of this, we designed a new CLF for robots capable of walking in any direction with any orientation, just like our Cassie robot. We also take into account features specific to bipeds, such as walking sideways is more costly due to the limited lateral leg motion. The left shows the distances versus behavior. The goal is fixed at 0, 0. I will place the robot at different distances, but fix the orientation. You can see that when the robot is far away from the goal, the robot would first align itself with the goal and then move forward. However, if the goal is closer to the target, the robot will walk sideways to reach the goal. You might notice there are 3 different values of alphas. The alpha balances between turning and sideways walking. For example, with a low alpha value, the robot will turn, then walk straight. On the other hand, with a high alpha value, the robot will walk sideways and then walk straight to the goal. And the right shows relative heading angle versus trajectory. We fix the robot at 15 meters away from the goal, and we change the orientation of it. You can see the trajectories. And we pick one of the trajectories. You can see we have 3 control variables: longitudinal velocity Vx, lateral velocity Vy, and angular velocity omega. You can see the control variables smoothly converge to 0. On the left figure, we show the resulting trajectory of the control variables. We derived an analytical solution for the CLF so that the whole system can run in real time. Paths are just integrating the differential equation defined by the CLF. In other words, I'm defining a differential equation between 2 nodes in our T star. Again, you can imagine that there is a vector field that terminates at the goal. If the robot deviates, the vector field will automatically create a new path and steer the robot back to the goal at no cost. The integrated CLF paths are then evaluated by terrain properties. And we will discuss this in the next few slides. The LE model is essentially a linear inverted pendulum model parameterized with angular momentum. The trajectory is integrated by the control variables through the LE model. And this is the system that realized the CLF's T star planner in practice. Here we have 2 planning. We have 2 threads. One is the planning thread, and the other is the reactive thread, which is used to cope with robot deviation at 300 Hertz. And the local map in the planning thread is responsible for computing extra information or extracting semantic information from the global map, and then provide this information to the controller. This planner system is fully implemented on Cassie. To emphasize again, the omnidirectional CLF RT star computes the CLF between 2 nodes in the RT tree. The cost of a CLF path is evaluated based on the information provided by the local map. Here we show a quick animation demonstrating how the cost of a CLF path is computed. Given a start pose and a goal position, we have RT samples. Then the CLF connects two nodes in the tree. We then compute the cost based on all the available information we have on board. For example, we might have elevation, slope, texture, friction. You can see that the icy road with the cyan color has the highest cost because it is dangerous for cats to walk on. There are two orange color paths for muddy roads. Obviously, the lower one has a lower cost, and the higher one has the higher cost. But you can see that the higher cost of the muddy road is still lower than the icy road. Finally, we can see that the red color is the sidewalk and has the lowest cost among all the other types because it is the safest type for Cassie to walk on. To reiterate again what we have discussed so far, we propose a new CLI formulation for omnidirectional robots, and it's integrated with RT start running at 5 Hz. And the automatic replanning associated with the CLF is implemented in the reactive thread running at 300 Hz. Local map to account for different terrain properties and to evaluate the local motion cost of a CLF path. We first run the planner on simulated indoor maps that contains many holes indicated by the blue and contains many obstacles indicated by the blue boxes, and the maps are patchy or noisy. The CLF planner guides the robot to the goal without hitting the obstacle. Next, we evaluate the system on synthetic outdoor undulating terrains. The terrains are still patchy and noisy. You can see that there are many holes in the map. A different color stands for different heights. You can see that the robot successfully avoids high terrain areas and only walks on the valleys. I'd like to mention here that even though it seems like the global map is given, but only the highlighted areas provided to the robot at each time step, just like what we would have in practice. We also perform a few high-level missions in simulation. The maps are still patchy and contains many holes. We have a final state machine to detect if there is an intersection. In the left experiment, if the robot detects intersection, we tell it to turn left. If not, then go straight. So ultimately, you will go back to its origin. On the right is a similar experiment, except we tell the robot to turn right, so you'll go to the center. How do we know if the controller commands given by the CLF planner are actually feasible to Cassie? The left is the sim mechanics simulator in MATLAB, which simulates 20 degrees of freedom and 40 dimensions of Cassie. The right is the planning system in C++. We send the controller commands from the right to the simulator through UDP. If the commands from the planner are not feasible, then Cassie in the simulator will fall. At the end, it successfully reached to the goal without falling. Now, we have done many simulations to ensure that the reactive CLF planner is capable of achieving indoor obstacle avoidance, outdoor undulating terrains, and several high-level missions. And we also verified that the controller commands from the CLF are actually feasible to Cassie in a full dynamics Cassie simulator. Next, we are ready to do real experiments. Well, moving away from simulation to experiments requires a full system integration, which is a huge amount of work, but it has to be done. On the left is the experiment setup, where you can see there are several chairs and desks that are considered as obstacles. On the right shows the map built online while Cassie autonomously navigating around obstacles. The greenish and the cyan colors are the desks and the chairs. You can see that Cassie successfully navigates around the obstacles. We also conduct another high-level missions where we took Cassie to the second floor of the Ford Robotics building. On the second floor, there are 4 long corridors forming a rectangle. The video is sped up due to the length of the video, and the total distance is about 200 meters. And the entire environment is unknown to Cassie at the beginning. And you can see we have a finite state machine. We have a finite state machine that uses an intersection detector. We instruct Cassie to turn right if she detects intersection. And so ultimately, she can come back to where she started. And again, you can see the map on the left is being built online while Cassie walking autonomously. You might notice that the map, there are several regions, there are several walkable regions behind the walls or behind the obstacles. That's because there are many glass walls, and the Lidar measurements actually penetrate through the glass wall and mark them as walkable region. So to remove this region, we apply the Brancham algorithm to remove those areas behind the glass wall. Once again, we need to have all the components running properly to have these autonomy experiments. And that includes sensor fusion, grade controllers, state estimators, and mapping algorithms at the end. And definitely human resources. So here you can see, or sped up pretty much because it's pretty long, the video. Yeah, so you can see Cassie turn right. And this is the last corridor. And here is actually the robot hit the wall a little because the motor failed, and the planner successfully guided back to the center of the corridor. Now we're going to return to where we started. You can see we have a lot of people just handling these autonomy experiments. So I guess you don't need to worry that the robot will chase you. So here you can see that we complete the map and we finish the high-level mission to turn right at every intersection. And at the end, return to its where we started. So we also took Cassie to undulating terrain, the wave field. We showed this video at the beginning of this topic, so we will not show it again here. To summarize, we integrate the CLF into the RT star planner, and the automatic replanning is implemented as a reactive thread running at 300 Hertz. We also have a multi-layer local maps to account for different terrain properties so that we can compute locomotion costs for our Cassie robot. Again, because of the CLF, we do not need to do waypoint following. We directly send 3 controller commands to Cassie. And a finite state machine is used to handle different high-level missions. All the codes is multi-threaded in C++ and is available online. In the future, we would like to replace the finite state machine to another higher level path planner. To conclude this dissertation, we have introduced the blocks of sensor fusion, pose estimation, and reactive motion planning system. Last, but not the least, I would like to thank my advisor, Jesse. You have shown me not only how to do research, but also many things in life. Additionally, and definitely, all the people in the biped lab and the friends and families. Also, in the journey of my PhD, I've mentored many master students on different topics of their interests and provided them opportunities to gain hands-on experience on real robots. Some of you guys are here. I hope you learned things that are helping your career. I can definitely say that you guys helped me achieve my goals. Thank you all.